This section, 3.1, is looking at quadratic functions. So in this part of the class, we're going to take a look at a few families of functions, and we're going to say, well, can we identify what their basic shape is, and then can we come up with some properties as far as that particular family of functions. So first we're looking at quadratic functions. So you see here the highest exponent, the degree is 2. So that tells me I have a quadratic function. I know its graph then is a parabola. So I might have a parabola that opens up, parabola that opens down, generally speaking. Okay, now the high or low point, typically we give the letters h, k to the x and y coordinates, and that's called the vertex of the parabola. All right, so what are we to start out with here? Well, we're going to take this quadratic function, we need to put it into what's called standard form. So, let me write here what that standard form is. So the standard form looks like a times x minus h squared plus k. Now we like this nice standard form because this gives us the vertex of the parabola. We can actually read off the letters h, k, and we have that information immediately. Okay, so that's why we like standard form. So this is the standard form. Okay, so my goal is, again, can I take this guy? Can I put it into standard form? So I need a series of steps. So my steps to put this into standard form, I'm going to use a process called completing the square. So here's the way I think about this. Here are my steps. Step 1, say move the constant to the side opposite the x. So in other words, you see the constant here. The constant is the term that has no variable, so the number there without the variable attached to it. So that's the constant. So step 1 is going to be move that to the side opposite the x. So I'm going to have y minus 24. So it looks like that, step 1. Okay, step 2. Divide by the lead coefficient, if not 1. In other words, I have to have a 1 in front of the x squared. You see how in this case, I actually, already have a 1 in front of x squared. So if there were a number there like 2, say I'd divide both sides by 2. All right, we'll talk about an example like that later. In this example, there's no number multiplying the x squared, just a 1. So that step is done. Okay, here's step 3. Add the special number. So the special number is b over 2 squared. I have to add this to both sides. Okay, so what does that mean? So when I'm looking at this, typically we think of this as being like ax squared plus bx plus c. Okay, so the b is the coefficient on the linear term, the coefficient on just the x. Okay, so this is the b. All right, so I have to do this side calculation then. So I set up on the side. So that special number is 25. So what I'm going to do is I'm going to add that number on both sides. Okay. Now what? Now the reason we do that is because once we've done that, this expression, this trinomial on the right here, it always factors as a perfect square, which remember, that's what I'm looking for back up here to get my standard form. Okay, so now I factor this expression on the right. So look, I can say what adds to -10 multiplies to +25. That'd be -5 and -5, right? So that'd be x minus 5 squared. So actually, I could really skip that middle step, and I could say, well, look, the number in here, if I double it, it has to make the b, right? So actually, I could tell you immediately, if I'm factoring something like this, since I know this is a perfect square, I could tell you immediately the number in here has to be half of this number. Has to be -5. And then think about it. -5 minus another 5 is -10. -5 times -5 is +25. Okay, now subtract the 1. And then we have it. So maybe in the last step, I'll write this in functional notation. So I'll write it as f of x instead of y. Okay, so there's my parabola, quadratic function written in standard form. Then I should be able to go ahead and tell you the vertex by reading off the HK pair. So now I'm comparing this with this. So look, the H is the number being subtracted, 5. The K is the number being added. So this is like plus -1. So I just carry that sign. So here's a little trick for reading off the vertex if you think it's tricky with the signs. So what I do to get the x coordinate, I think about what number would make the inside of this parenthesis 0. Be 5, right? This number, I just bring it along as it is with its sign. And then I have the vertex. Okay. So there's that piece of information. Then I was also interested in creating a graph. Let's move this down. Get that out of the way for now. All right, so should I start graphing this? Let's see if that works. So first piece of information, I'll put the vertex. 1, 2, 3, 4, 5, -1. Okay, does the parabola open up or down? So actually I can determine that by looking at the lead coefficient. So you see how the lead coefficient here is 1? I can look here or here. In other words, the A is positive. That means the parabola has not been reflected. So that means the parabola opens up. If the A were negative, that parabola would be reflected down and it would open downwards. So I know it opens up. So I mean, I have something like that, okay? I'd like to do a little bit better job graphing it. So let me see what other information I could find. Here's something that's useful. we like to look at intercepts. Let's start with the y-intercept. Okay, so remember to find the y-intercept, I'm looking at where does this cross the y-axis? In other words, where is the x equal to 0? Now, actually, I can use either equation. So I can use the original equation here or the standard form. Actually, for this calculation, if I'm setting x to 0, wouldn't it be simplest to use this equation? Because if I set x to 0 there, I can tell you immediately both of the first two terms zero out, and I'm just left with 24. So that's my y-intercept. My y-intercept is 0, 24. Now that's going to be way up here on the y-axis. So I have the information. I don't know if I'll put that on the graph for now. Let me see if I can do without it. Maybe the x-intercepts would be more useful. So for those, I'm looking at where does the graph cross the x-axis? So in other words, I'm setting y equal to 0. So for that, again, I can use either equation. I can use the original equation or the standard form. So what will happen if I take the original equation up here and I set it to 0? So I'll have x squared minus 10x plus 24 is 0. So what are my options for solving that? Well, I guess the first thing I would try is I'd try factoring it. Now, if that factors, this problem's actually really pretty easy. If it doesn't factor, though, I would be stuck using the quadratic formula. Okay, so in this case, let's see, I think this factors, so adds to negative 10, multiplies to positive 24. Let's try negative 6 and negative 4. So these are my x-intercepts. Okay, I guess I'll go ahead and put those on the graph. But then I was going to ask, well, so this one was pretty easy because it factored. So if it did not factor, actually in that case, it's easier to use the standard form equation here. So let me look at finding the x-intercepts that way. So if instead I had set that equation to 0, how would I solve that? I guess I would add the 1, take the square root. Now remember, when you take the square root, it's plus or minus in front. Square root of 1 is 1. So that says either x minus 5 is negative 1, or x minus 5 is positive 1. So x is 4 or x is 6. So you can see I get the same x-intercepts. Okay, so in this example, I mean, either of those approaches actually pretty easy. But like I said, if the original equation does not factor, then it's nicer to use the standard form to find the x-intercepts. Okay, so what else can I do with this? I put the x-intercepts on the graph. Let me add something else in here. So if I dash in this vertical line through the vertex, go ahead and clean this up. If I dash that vertical line in, that's the line over which the parabola is symmetric. So we call that, you could say, the line of symmetry, or I believe this book says this is the axis of symmetry. So that's a vertical line. So it's of the form x equals a number. So wherever I am on that line, isn't the x always equal to 5? So wouldn't that equation of that axis of symmetry always just be x equals h, x equals the x coordinate of the vertex? So that's a piece of information I can include. So let me go ahead and draw the graph then. It looks something like that. Okay, so the parabola is symmetric over or with respect to x equals 5. Let's do one more thing. So it's the domain. So let's see, for quadratic functions, the domain is very easy to find. It's just all real numbers. Extends all the way across horizontally. The range, however, look, the lowest I can go on this graph is -1. So the range would be -1 to infinity. Oh, I don't know. Should I even do one more thing? Maybe I'll do one more thing. To see if I can move all this down. I wanted to make some more room. Nice. Okay, I wanted to do one more thing, which is look at, let's say f of x is increasing. I want to say on what interval is f of x increasing, and on what interval is f of x decreasing. So that means if I start on the far left, and I'm moving along the parabola, look, I'm going down, 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 down until I get to x equals 5. So I would say the parabola is decreasing from -infinity to 5 versus after x equals 5, I'm going up, 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 up. So then I would say it's increasing from 5 to infinity. I guess I could say this parabola has this one has a local min of -1. This guy has a local min of -1 at x equals 5. Okay, so just different information I can read off about that quadratic function. Okay. So what's next? Okay, so here's another one. Same instructions. Let's start by putting this in standard form by completing the square. Okay, so remember the first thing we do, we move the constant. So y plus 2 is -3x squared minus 12x. Now you'll notice that this function actually has a lead coefficient. So I have to divide both sides by -3 because I need a 1 in front of the x squared. So I would just leave that left side as it is. The right side, go ahead and divide both terms by that -3. Now I can find my special number. So remember how that works. That's b over 2 squared. Now I have to use the b from the step after I've divided, so from the latest step. Okay. So the special number is 4. So I go ahead and add that on both sides. Again, the left side, I would just leave it as it is. I mean, if I wanted to combine the 4, I'd have to do an LCD. Why bother? So let me go ahead and factor this. Now remember that trinomial on the right, it always factors as a perfect square. So the number inside has to be half of b. So wouldn't it have to be positive 2? Let's see, 2 plus 2 is 4, 2 times 2 is 4. So now I have my square, I just need to move everything back over. Let me start by subtracting this 4 then. Okay, then I'm going to multiply by negative 3. Make sure you multiply both terms. Last step, subtract the 2. And then I'll write it as an f of x, functional notation. So there's my standard form. Let me read off my vertex, h comma k. So the number that makes the inside 0 here is negative 2. The k is just 10. There's my vertex. Okay. So let's go ahead and do a graph for this one. This down. Put that out of the way for now. Negative 210. Okay. Set that up something like that, maybe. Okay, there's negative 210. Okay, look at the lead coefficient. The lead coefficient's negative. I can look there, or I can look back here at the original equation. So either way, because that lead coefficient is negative, or because the a is less than 0, I know this parabola opens down. It's going to be something like that. Let me see what other information I can get then. Let me get the y-intercept. Set x to 0. So I can use the standard form. For the y-intercept, it's actually easier to use the original equation. Let me copy this down. We have both of these to look at. So I'm going to use that. Okay, so if I plug 0 in there, I can tell you immediately the result is negative 2. That makes that calculation actually really easy. Okay, let me find the x-intercepts. Okay, so if I set the whole function to 0, so again, I can use the original equation. If I set that to 0 though, actually this one does not factor. So I would actually have to use the quadratic formula. You remember that one from like middle school. So I prefer to avoid using the quadratic formula if I can. In other words, I would rather take the standard form equation then and set that to 0. That way I can avoid dealing with the quadratic formula. Okay, take the square root. So plus or minus root 10 over root 3. Now we don't like to leave square roots in the denominator. So what we'll do is we'll rationalize the denominator. We'll multiply it by root 3 over root 3. That's just to make this look a little nicer. Of root 30 over 3. And then I can subtract the 2. Okay, now usually what we do with intercepts, since those are points, we like to write them as coordinate pairs. So I could do that. So I'd have negative 2 minus root 30 over 3 0, negative 2 plus root 30 over 3, 0. Now those don't come out very nice, but that's still an important piece of information to include with my calculations. So, well, how else could I come up with a graph then if I don't want to use those points? What if I put the axis of symmetry on here? Remember that goes through the vertex. So wouldn't that equation be x equals negative 2 then? So couldn't I use that to find a mirror point? I mean, what if I take this point and I say, you see how that point is 2 units right of that axis of symmetry? So based on that symmetry, doesn't there have to be another point 2 units left here? So doesn't there have to be a mirror point at negative 4, negative 2? So now I have enough information to actually draw that graph. Okay, try to make it look symmetric. Okay, then you can see, I mean, I have these intercepts. There's one here and one here, but they're not an integer. They're not a whole number values. So that matches up with the x-intercepts that we found. Okay, well, let's do one more thing. I don't want to do too much more with this one. Let's find the domain. That's the easy part. What about the range? Negative infinity to 10. Okie dokie. Now, I want to do one more. I don't want to do the whole graph and everything, though. I'll just do the completing the square part. Put this in standard form. Just because I wanted to show you one where we're dealing with a fraction. So move the constant. Divide by the lead coefficient. Divide both terms. So you see how in this one, the b is actually 1. So a half squared is a quarter. So my special number that I'm adding on both sides is actually a quarter. Okay. To add it on both sides. Okay, and then factor. Now remember, the number inside here is always half of b. Half of 1 is a half, right? So a half plus a half is 1, a half times a half is a quarter. So actually that's not hard to factor. Then I just move everything back over. So subtract the 1/4. I don't know if I'll try to squeeze it in there. I guess I'll move this stuff again. And leave enough room. That's okay. Okay. Go ahead and multiply everything by 3. So y minus 1 is 3 times x plus a half squared minus 3/4. Then add the 1. So 1 is 4/4. What is that then, a quarter? Okay, and then the last step is f of x equals. So there it is. I guess the vertex be negative a half, a quarter. Okay, so not too bad, even with the fractions. All we get to look at a couple of these in word problems. This is the last one. Okie dokie. I have 5,000 feet of fencing to enclose a 3-sided rectangular field. So I don't know, maybe there's a river or something here. I'm not fencing that side. Fencing 3 sides of this rectangle. So 2 X's and a Y, say? What dimensions maximize the area? What is the maximum area that can be enclosed? Now, of course, I'm supposed to use algebra to answer this question. So I would start by setting up a couple of equations. So let's see what I know. I know I have 5,000 feet of fencing. So I have to enclose, let's see, there are 2 X sides and 1 Y side. So those 2 X's plus a 1 Y has to add to 5,000. The other thing we're interested in here is the area. Okay? I know the area of a rectangle is length times width. So I really have a little system of equations here. All right, so what am I going to do next? I'm going to say, well, the thing is, I really want to maximize the second equation here, this one. But I have 2 variables in there, so my goal is to maximize that equation. But because I have 2 variables in there, I'm kind of stuck at the moment. I can't really do much with that. But what if I do a substitution? So what if I do substitution, because I need to use the first equation. So what if I solve the first equation for, say, y? And then I take that and I plug that into the second equation. So then wouldn't the second equation look like I have an x in front and then times my 5,000 minus 2x? So my area as a function of just x, I'm rearranging, looks like this, right? Now, why is that helpful? Well, because now I can see what kind of shape I'm dealing with as far as that area function. So what do I have? I have a parabola with a negative lead coefficient. So what do I know? I know I have a parabola that opens down. So what can I tell you? I can tell you the max is going to be at the vertex. So really this problem is just asking me to find the vertex. Okay, so actually I know how to do that. I mean, I can do this problem by completing the square. Or there's actually a shortcut formula to find the vertex. Okay, so let me show you this. So if I have, my parabola, ax squared plus bx plus c, the x coordinate of the vertex is negative b over 2a. After I've found that information, I have to plug the x in to get the corresponding y. Okay? So this is my vertex shortcut formula. This is the part you really have to remember. So if I'm looking at my area equation, I think this would be an appropriate time to use that shortcut formula. Okay, here's the B, here's the A. Okay, so x equals negative b over 2a. see, 5,000 over 4. So what the heck is that? 2,500 over 2. Half of 2,500, is that 1,250? Okay. So what did I find? I found the length of this side x here, for which the area of that rectangle is going to be maximized. Okay, how do I get the matching y value? Well, remember that the 2 x's plus the 1 y, that has to add up to that total of 5,000. So couldn't I use this equation? Wouldn't that just be then the 5,000 minus 2 times 1,250, which was 2,500? So wouldn't that have to be 2,500? Okay, so let me see if I can write a statement then. So the dimensions that maximize the area would be 1,250 by 2,500. Make sure you include the units, feet. Okay. Then what else did it ask me? It asked me, what is the maximum area? Okay, so I gotta move this one more time. So how do I actually find the maximum area? I can think of 2 ways. Well, the area is just x times y, right? So couldn't I actually just multiply that 1,250 by 2,500? So that's one idea. So it looks like that'd be square feet. My other thought would be, well, I could actually take that, let me see, that x value, this one, and I could actually plug that in to my area function. Okay, if I did that, I should get the same result, okay? Well, I guess I'll let you check that on your own. Should I look back? I'm just curious about, like, I don't know, look at one of these other ones. I don't know, this one. So you see how in this one, this was our original equation. We did completing the square. Here was the vertex we ended up with. I'm just curious, maybe we should check, because I showed you that shortcut formula, right? I'm just curious, well, I could check one of these using the shortcut formula and just make sure we came up with the correct vertex. So how would I do that? I'd use the original equation. Okay, so what would that give me? That'd be 12 over -6. There's -2. Then I would have to plug -2 in. Oh, I lost my negative here. So that's 12 minus 2. Oh, look at that. I get the same result. Okay, so just verifying that that shortcut formula also works there to find the vertex that we already found by completing the square. Okay, so where were we? I'm going to do this last problem. This one's a little shorter, actually. The revenue generated from selling X items is given by R of X equals -4X squared plus 4,000X. So this one actually already have the function, so I don't have to build the function. So I can see that this is a parabola, opens down. Okay, so in order to find the maximum, I'm looking again for the vertex. Okay, so how about I don't know. Should I try this one by completing the square? I could use the shortcut formula or completing the square. Let's try it this way. So there's no constant, so nothing to move to the other side. So I would go ahead and divide. Okay, then I would go ahead and find my special number. Okay, so let's see. 500 squared. Then I would factor. So it has to look like this, right? It's 500 plus 500 is 1,000. The negative, then let's see, negative 500 times negative 500 is 500 squared. So then I just move stuff back over. Okay. So I mean, I have it. I don't know, at this step, maybe I want to go ahead and figure out what this quantity is, huh? So if I'm not using a calculator, I like to be kind of clever in how I do these multiplications. 20 lots of ideas for how you could do this. 2 times 500, so I have 1,000 times 100 times 10. It's this times this times this times that. So 1,000 times 100 times 10. Okay, looks like 1,000,000. Okay, so let me write that in then. And what the heck was this? This was the R of X, the revenue function. Okay, that's just scratch work since I wasn't using a calculator. So there's my standard form. So then what the heck was I supposed to answer? How many items should be sold to maximize the revenue? So in other words, what is the X value? So the X would be 500. So 500 items to maximize the revenue. Okay, and then what's the next question? Well, let's answer this then. Let's answer, I guess I didn't ask. The max revenue would be, well, the 1,000,000. That's the Y coordinate. Okay. So I could have used the shortcut formula, and that probably would have been a lot easier. I wanted to show you doing one like this. So I don't know. What if I start it over and I say or use the shortcut formula? And so what was, this was the original function. And then I was just thinking, well, why don't we check that? Why don't we see how you would do that if you would have used the shortcut formula instead? Well, look at that. There's that 500 items. Looks like that was a lot easier to find. And then to get the revenue, I would have plugged the 500 in here. And then I'll let you verify that comes out to be that million again. So that's the other idea. So sometimes the instructions will say use completing the square. So I wanted to show you one where we did the problem specifically that way. Sometimes it doesn't say, and then you can use the shortcut formula. Okay, I just wanted to do one more thing. How many items must be sold to produce no revenue? So in other words, wouldn't that be asking when is the revenue equal to 0 for there to be no revenue? So I'd set that up like that, right? That's actually really easy to solve. Can't you factor out a negative 4x? So the values look like 0 and 1,000 items. Well, that kind of makes sense because I could think of even another way to determine that. Because just look for a second. So I'll use the ruler. What would happen if I went to graph R of x? Okay, look at the function for a second. If I plug 0 in here, I get 0, right? So in other words, the y-intercept is 0. Look at the other piece of information I found. I found that the x-coordinate of the vertex is 500. So doesn't that mean the peak is at 500? So if this is symmetric, which it has to be, doesn't the next 0 have to be at 1,000? So wouldn't it make sense then that parabola looks something like that?